right, we are recording. Okay, so let's do some log practice. Why don't you jot that down on loose leaf right now? Let's do 1A here. Express the exponential identities in logarithmic form. So let's do that one. We'll do 5 squared equals 25. So here we go. So example, pen, come on, work. There we go. Example 1, 5 squared equals 25. Express that in logarithm form. What does that look like? Well, the base of my logarithm is the 5. 25 is my argument, and 2 is my answer. That is the same exact equation written in its inverse form, called logarithm form. If you want to say that in words, this is what this says in words. If I take a base of 5, I will reach 25 after multiplying 2 of them together. That's the way I think of a logarithm statement. If I take a base of 5, I will reach 25 after I've multiplied 2 of them together. Here, let's color code that. 5, 25, 2. There. Ooh, isn't that fancy? So there's example 1. That's what it means to do a logarithm. Okay, let's pick another one. Let's do, let's do 1e. So let me say that again. 27 to the 2/3 equals 9. So next example. 27 to the 2/3 is equal to 9. What does that look like in logarithm form? Okay, I'll give you a sec. Give it a try. People at home, give it a try. You get it? Did you get log to the base of 27 of 9 is 2/3? That's the answer. And again, we call that a base. We call that an argument. And in this case, this is my answer, I guess, but it's also the exponent. And what logarithms allow us to do is something that we've never really been able to do in math up till now, which is solve for unknown exponents, right? Like, for example, let's see, there's some on this page, right? Log to the base 2, I'm going to look at 3b. Log to the base 2 of x equals 3. Log to the base 2 of x equals 3. Right? So how do I solve that? How do I figure out what x is? Well, let's put that into the exponential form. 2 is my base, 3 is my exponent, x is my argument. So basically, no problem, x is 8. Okay, so that's one type of question. Let's pick a different one. How about evaluate log to the base 2 of 16? Let's just do 4a. Evaluate log to the base 2 of 16. So here, how do I do that? This is, again, this is what I was saying a minute ago. This is the kind of stuff you were unable to do before unless it was easy. Now this actually is an easy one. 2 to some power of x is 16. Now, in days of old, if that was where you were at in your arithmetic, you basically had to guess and check. So skip count by multiplying. 2 times 2 is 4, so that's 2 of them. Times 2 is 8, that's 3 of them. Times 2 is 16. So the answer to this is that x is 4. But what if it wasn't one I could count to? What if it was 2 to some power equals 20? Well, up till now, the only real strategy you had for this was what? Well, guessing and checking still. What I call the Goldilocks strategy. I know that 2 to the 4 is 16, and I know that the next power of 2 is going to be like way up at 32. So I know that it's somewhere between 4 and 5. X is between 4 and 5. That's what I know. But what is it exactly? Well, I could spend a lot of time saying, well, is it 4.5? Is it 4.6? And then when I go, oh, it's somewhere between 4.5 and 4.6. And then I just keep on trying smaller decimals till I get closer and closer to the answer. That's the only real strategy we had for a question like that. Now we can change it to log to the base 2 of 20 equals x. Problem, how do I figure out log to the base 2 of anything? Well, it depends. So that's kind of where today's lesson is going to go. We're going to go into some calculations and things called log laws. Let's maybe, before we get to today's lesson, let's maybe do 1 or 2 more from this sheet. These estimate ones are basically what I was just talking about. Number 6, don't bother with number 6. We're not going to do any sketching. But you can do, here we go. Let's do 4. Oh, and you're probably wondering what the heck this means. That'll pop up in future lessons. Don't worry about that right now. Let's do 3e. 3e is cool. Log to the base x of 8 equals 1. How much is x? You can probably guess this already. All right, so let's see. Let's go back. Did I copy that right? Log to the base, yep, log to the base x of 8 is equal to 1. So in other words, think about this in exponential form. A base of x to an exponent of 1 is 8. What must x be? X must be 8. In fact, I think we've probably got ourselves a rule here. What does that have to be? That has to be 1. Assuming, of course, x isn't 0. For every other number in the universe, that's a rule. Right? Because think about it. Change that to exponential form, and you're saying x to the 1 equals x, which is a true statement. Oh, actually, wait a minute. I guess it does work for 0 too, doesn't it? You know what? I'm going to say mulligan on that. Cross that out. That's not true. This is true for every number, including 0, because... So we could call that like a rule, a law for logarithms. That has to be true, doesn't it? So there are laws for logarithms. That's what we're going to do for the rest of this class. We're going to take a look at some laws of logarithms. So again, this is like an extra practice page of stuff. It's got an answer key. Actually, the answer key is right under here. Upside down, because that's the way my scans happen sometimes. But let's go now to your notes booklet. Hey, how's Augustine doing? Oh, okay. Oh, Santa came here. So what's happening with those?
Well, we'll tuck them away in case these break.
Okay, so put them in the math office in a closet or something?
Yeah.
Yeah, that's a good idea probably.
Yeah. Hopefully these are.
Yeah, I'll play with it. I have a prep after lunch. I'll play with it then. Okay, thanks. All right. Hear that? Put this thing in the graveyard. All right, so we're going to do some notes. Can everybody go to chapter 8, lesson 3? We're going to skip lesson 2. We're not going to graph logs. Again, exponential graphs are already done. And before we actually start these, you don't have to write this down, but do you remember your laws for exponents from grade 9? Let's see if we could remember these. Again, you don't have to write this down, just kind of think it through with me. I'll use green. X to the a times x to the b. If the bases are the same, what do you do with the exponents? Add them. Correct. If the bases are the same and you divide, what do you do with the exponents? You subtract them. A minus b. If you take the power of a power, what do you do with the exponents? You multiply them. These had names too, by the way. This one was called the product law. This one was called the quotient law. I don't really care if people remember the names. This one has a very creative name, power of a power law. This one was called power of a product. And this one was called power of a quotient. And if you remember how these work, what can I do here? If I'm taking a product, that means numbers times together, to an exponent, what can I do? I can distribute the exponent. Right? And same thing with a quotient. If I'm dividing two things and that's all to one power, I can distribute the exponent. Power of a product, power of a quotient. There is no such thing as power of a sum or power of a difference. It would, in fact, be wrong to say this. Right? That is incorrect. It has to be a product or a quotient in here to distribute the power. It doesn't work for adds and subtracts. So let me get that up there. Okay, grade 9 gave you one more law. Oops. There we go. Grade 9 gave you one more law. What's x to the power of 0? 1. This one, of course, does have a caveat, though. It says x, of course, can't be 0. For every other number in the universe except 0, 0 to the power of 0 is not 1, but every other number in the universe to the power of 0 is 1. So that's the laws that you got in grade 9. Then we added to that a little in grade 10. Do you remember what this means? What happens if you take a negative exponent of base x? It's 1 over x to the a, correct? And what happens if you take a fractional power of base x? It is the eighth root of x. And so there's the rest of them. So that's it. That is all the exponent laws that really you have. Every single one of those has what you could call a inverse of it as a log law. So the log laws are actually based on these exponent laws. Okay, so let's start writing now. Go to 8.3. Put that into black. And all right. This one is, of course, again, kind of like a product law. It says that if I have the log to the base a of mn, and we understand that everything to the right of the log until you hit a plus or a minus is part of the same argument. So basically this says log to the base a of mn. We assume a bracket here. We don't do this in most areas of math. In most areas of math, you don't assume a bracket if it's not there, right? Many, many times I have taken marks off of students because, let me go back to red, because they do silly things like this. They'll say, that's 4. And I'll say, no, it isn't. It's only 4 if there's a bracket there. And they'll say, oh, I didn't bother writing it, but I knew that's what I meant. Well, you can't do that. And then they'll do something like 2x plus 3 times x plus 4, and they'll forget to put the brackets around this one. And then they'll tell me that that's 2x squared plus 11x plus 12. And I'll say, this doesn't equal this. You're not multiplying the 2x by this bracket. You're only multiplying the 3 by this bracket. And they'll say, oh, well, I meant for there to be a bracket here. I just didn't bother writing it down. Well, to those people who have lost half marks in those types of situations, I have good news for you. Finally, we've hit a place in math where we can just assume the bracket's there and not say it. Okay? This is part of the argument. You always assume it's one argument until you see a plus or a minus. Okay? So there we go. So what can I do with this new law? Well, log to the base 2 of 6 is like saying log to the base 2 of 2 plus log to the base 2 of 3. What? Why does that happen? Because 2 times 3 is 6. And you might be wondering, well, I don't know what the log to the base 2 of 3 is, so why is this a helpful thing? Well, it's helpful in the sense that you know that log to the base 2 of 2 is just 1, because we just talked about that, right? Because remember, this thing's saying, if I times 2's together, how many does it take to get to 2? The answer is 1. This I'd have to actually get some sort of calculation going. And we'll show you later today how to do those calculations. Okay, so there's log law number 1. A multiply can be split up into an add. Multiplies make adds in logs, which makes sense because, again, what is multiply? It's repeated add. Why did you learn what 5 times 7 is and memorize that it's 35? Because it's a lot less work than adding up 5 7s. 7, 14, 21. Blech. Right? That's what multiply is. We invented it so we could skip count adding. We invented exponents so we could skip count multiplying. Okay, this is deep. Next law. Just like the second law, the second exponent law was a divide one, the quotient law, the second log law is also a divide one. And in this case, a divide turns out to be a subtract. So this thing can be said to be log to the base x of 8 minus log to the base x of 3. All right, third log law. What happens if you have an exponent in a logarithm statement? The exponent, right here, little x, becomes a coefficient. So in this case, first I'm going to change this into something a little more exponential. Log to the base 3 of 6 to the power of a half is like saying a half times the log to the base 3 of 6. That's an O. That looks like a B. Looks like a real bog. Let me make that pretty. There. Okay, and the fourth law might be our most useful when it comes for calculating. I said a minute ago, I don't really know what log to the base 2 of 3 is, but I can figure it out. We call number 4 the change of base law, and it works like this. Notice that we have, let me move the screen up a bit. Notice that we have log to the base a of x, and then I can say that that's log of x divided by log of a. Now, what happened in these, what happened here? How come I don't see a base there? We learned this yesterday. When we don't write a base number down in a logarithm statement, we are assuming that the base is 10. Makes sense. Our whole number system is based on a base of 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then move over a place, slap down a 0. We count by tens. So our whole number system is essentially a power of 10 machine. So when we do logarithms and we're using the base 10, we don't need to bother writing it down. So, if that makes sense to you, log to the base 2 of 7 is like saying log to the, oh man, once again, that's an ugly log. Log to the base 10 of 7 divided by log to the base 10 of 2. And again, let's make sure that we understand what this is saying. If I had to try to find log to the base 2 of 7, say that I'm trying to find that number, so I'll call that number x. That means I am solving the equation 2 to the power of x is 7. And once again, up till now, the only way that you could have dealt with that is to guess and check, right? Because what do you know? You know 2 squared is 4, and 2 cubed is 8. So my answer is somewhere between 4 and 8, right? It's going to be an irrational decimal of some sort between 4 and 8. Now I can find it exactly without guessing and checking, because I can actually do that as log to the base 10 of 7 divided by log to the base 10 of 2. Take your calculator out and try it. What should we get here? So let's actually punch buttons. Log to the base 7, or sorry, log to the base 10 of 2 divided by log to the base, let me say that again. Log to the base 10 of 7 divided by log to the base 10 of 2 on my calculator is, let's see, where is the log button? Every calculator's a log button. Log of 7 divided by log of 2, and I'm getting 2.80735 and a whole bunch of decimals. Right? Some calculators give you 9 decimals, some 10. I think there's even a couple that give you 12. Did that work? You got that? Okay. Remember how to use your answer button? Remember I showed you how to use the answer button when you're doing trig and stuff like that? See if that's true. According to our calculations, that should be the x in this equation. So why don't you see if that actually works? Go 2 to the power of that 2.80735 blah, blah, blah. It should be exactly 7 if you don't round it. So go 2 to the power, and if people are having a hard time finding their power button, let me know. I can come and show you. To the power of my answer. I have an answer button. Everybody who has a scientific calculator should have an answer button. There is, if there's no answer button, you have like a less fancy calculator, you have a memory button, and you can just put a number into memory, store it, and then bring it out. If you don't know how to do that, I can show you. And then hit equals, and yep, it should be exactly 7. Did that work for you? So there you go. You've learned how to do something today that's been flummoxing you for ever since you first learned exponents. How do you solve for an exponent as a variable when it's not something I can count exactly with my times table? Right? 2 to the x equals 16, no problem. X is 4, because that's what 2 times 2 times 2 times 2 is. But 2 to the exponent x equals 7, it's 2 point something. Well, now you can figure out that point something. I want to say exactly, but of course, even this answer is not really exact, right? Because it's a decimal. It's irrational. I'm rounding it somewhere. Okay, notice, okay, these notes are old. The log button on a calculator is base 10. When you press the button that says LOG, it's 10. Therefore, this button can only be used to find solutions with a base of 10. That's why we kind of need this little formula. For example, log to the base 2 of 7 cannot be entered into the calculator. Now, I've been here. This is my 4th year here. When I saw these notes 3 years ago, they probably put these notes together about 6 or 7 years ago when they made all those fancy videos that are on the school's website. I said, you know, maybe we should update these notes because I think I had a calculator just like this. Fancier calculators actually do have the ability for you to punch in log to the base 2 of 7. If you actually have a calculator that has a button that says this, you don't have to write this down. This calculator has a button that says log, and then there's a little blank, and then there's a bigger blank. If you have a calculator with that button, like this kind, you actually don't need formula number 4 because you can do this without it. Okay? TI-83s don't do that. TI-84s don't do that. But if you have the TI-84 Plus, you can do this. It's actually in the menus under Math, but you can do that. So if you have one of those big fancy graphing calculators, if it's a newer one, you can do it. If anybody does have that button, you just press the button, and then you fill in the 2 and the 7, and boom, there's your 2.8 number again. So yep. So I'm gonna say, give me a pen. What's going on? Did I freeze? There we go. I'm gonna say some calculators have this. And if you don't, you need a formula. Okay? Any questions about that? All right. What? Check that thing out. Simplify the expression 2 log x minus, big bracket, log y minus 1/3 log z. All right, what am I doing? Step 1 is I'm going to distribute the negative. I want that bracket to go away. So that's going to be 2 log x minus log y plus 1/3 log z. And if you're like me and your z's can look like 2's if you're not careful, put a little tick through your z. Okay, there. Does everybody get what I did in the first step? Distributed the negative? That's easy. Now I'm going to use my log laws. What did log law 3 tell me? Log law 3 told me coefficients and exponents are the same thing in logs. So this is like saying log of x squared. I can do that again. Where can I do that again? On the third term. Now I'm going to use laws 1 and 2. I might actually rearrange it, though. I might think of it. I don't think if I was doing my homework I'd bother writing this down. But I'm just going to rearrange it. And why did I do that? So that I could, I'm kind of out of room here, so I'm just going to go that way. So that I could change this to log of x squared y over z to the 1/3. Or I might like that answer this way better. Oops. There, used a power law too. Now, which one of those is the most simple answer? I don't know. This is usually where some wise guy goes in. Don't we want to rationalize the denominator? We could. This can be one of the challenges of this, this type of work. When you start working with exponents at higher levels, whether you're using logarithms or even just questions that have heavy exponents in their algebra, there can be lots of different ways to express a final answer, and it's not really a hard, fast rule as to which one's the most simplified. If anybody in this class was in my intro calc, I have some people in the other section who are doing the intro calc too, they will tell you exactly what we mean. We just actually did a quiz where I actually put in big bold letters, use the chain rule, and do not simplify, because I don't want to have 30 different quizzes that all simplified a little bit differently that I got to try to get through to see if you have the right answer. So which one of those two answers is most simplified? No. Take your pick. And somebody again might look at the second one here and say, but I want to rationalize this denominator. I don't know what's going on. I wonder if my pen is, is the battery dying on my pen? There we go. Having some troubles with my pen. Okay, anyway, next. Maybe before we leave this, I'm just going to say, I'm going to say once again, pen. I'm going to say simplify often means express as a single logarithm. Expand is the opposite. That's one big logarithm. I would like to expand it as much as possible. So let's expand it. All right. It means that we can take log to the base of A of capital A. These two things in here are a multiply, right? Can you see where I'm pointing? Probably not. Let me undo that. Right? Those two things are times together. And in logarithms, a multiply makes an add. And of course, a square root is an exponent of a half. And then I'm minusing everything that's in the bottom. So that's log to the base A of B squared plus log to the base A of D. Now, can we agree that that's not as simplified as it can be? First of all, there's another log law I can use. exponents can become coefficients. So I'm going to do that. The second thing I can do is I can get rid of the bracket. So I'm going to do those two steps at once. So that's log to the base a of a plus 1/2 log to the base a of c minus 2 times log to the base a of b minus log to the base a of d. There. That's as expanded as I think it can get. Okay, now that we've done it with algebra, let's do it with numbers. Remember when math used to be the other way? When it was like, okay, we've practiced this with numbers, now let's try it with algebra. Now the algebra is the easy part. Let's play with numbers. Simplify and evaluate the following expressions using the laws of logarithms. Okay, so simplify means get it to 1 log. So that's log to the base 6 of 8 and 9 get multiplied together and then divided by 2. What's 8 times 9 divided by 2? Oh, come on, that's not that hard. 8 times 9. What's your times tables going? Yeah, there we go. This is going to be 36. And hey, that's nice. If I multiply together 6's, how many of them do I need to get to 36? 2. All right, the second one's a little more work. First thing I'm going to do is I'm going to turn this 2 at the very beginning from a coefficient into an exponent. So this is log to the base 2 of 12 squared. Minus, I'm going to distribute the minus. So that's log to the base 2 of 6 plus log, oh, sorry. Minus log to the base 2 of 27 to the power of 1/3. Let's just make that a radical. Cube root of 27. I said cube root, and then I didn't write my 3. There we go. Okay, now what? Now I'm going to use my log laws, right? My log laws say that if I'm subtracting, that becomes a denominator, right? That becomes a divide. So this is log to the base 2 of 12 squared all over 6 times the cube root of 27. And now I'm just going to evaluate. So that's log to the base 2 of 12 squared, that's 144, over 6 times, and the cube root of 27 is 3. So this is log to the base 2 of 144 over 18. How many 18s go into 144? No, you can't have your calculator. Try splitting it up, right? 144 is 12 times 12, so there's a 6 there, right? So it actually, I think, ends up being exactly 8. So that's log to the base 2 of 8. All right, now you use your knowledge of logarithms. How many 2's you got to times together to get to 8? There we go. That's a fairly difficult one. So there we go. There's how that works. All right, next. If log to the base a of 2 is 0.3, and log to the base a of 3 is 0.48, and log to the base a of 5 is 0.7, find log to the base a of 150. Whoa. All right, here's what we're going to do. We're going to make that number 150 into 2 times 3 times 5 times 5. And if you're wondering how I did that, I'm actually looking at my notes. I had made a factor tree. Do you remember factor trees? And there we go. So that's how I figured it out. I used a factor tree. All right, I'm going to maybe now change that to log to the base a of 2 times 3 times 5 squared. And now I can use my log law. Multiplies and adds are the same thing if I distribute the log. So that's log to the base a of 2 plus log to the base a of 3 plus, I'm going to do two log laws at once. I'm changing this to a plus, and this exponent is going to become a coefficient. And then I'm going to put in the decimals they told me. They told me log to the base a of 2 is 0.3, and they told me log to the base a of 3 is 0.48, and they told me log to the base a of 5 is 0.7, but there's two of them. So that's, I might have to do some scrap work. 0.3, 0.48, and 1.4, because that's what 2.7s are. So that's 8, 4 and 4 is 8, and 3 is 1, carry the 1, 2.18. There you go. All right. Next, what do I do with that? Log to the base a of root 10 over 3. Okay, so once again, I'm going to have to turn this into 5s and 2s so that I can use the facts that they gave me. So this is log. First, I might get rid of this radical and change it to 10 to the 1/3 and 3 to the 1/3. Remember, I'm allowed to do that because of my exponent laws. You can distribute an exponent through a division. And I'm going to change that 10 now to a 5 times 2. Oh, wait a minute. Is that a cube root? Oh, I'm sorry. Can you change that? I thought that was a cube root. It's a square root. Let me change all these to squares. My bad. Square root, square root, square root, square root, square root. Sorry about that. My eyes are playing tricks on me. Okay, now I'm going to use my log laws to separate this. So, the multiply can become an add. And the division can become a subtract. And the exponents can become coefficients. And then I can evaluate. Actually, you know what I'll do even before I evaluate? I can save some calculating. I could factor that 1/2 out so that I only have to deal with it once. There we go. Log to the base a of 5 plus log to the base a of 2 plus log to the base a of 3. So that's going to equal 1/2 of, what were the decimals again? Log of 5 is 0.7, the log of 2 was 0.3, and the log of, oh, oops, I made another mistake. Did you see it? I just decided to turn a subtract into an add for no reason. There we go. And what was the log of 3 again? 0.48. Okay, so let's do that. We can do this one in our heads, I think, because that's 1, right? 0.7 plus 0.3 is 1. 1 minus 0.48 is 0.52, and then 1/2 of 0.52. Wait a minute. Am I right about that? 1 minus 0.48 is 0.52, yes. And 1/2 of 0.52 would be 0.26. Somebody double check my mental math, but I think I got it. All right, next. What am I going to do with that thing? Log to the base, or log to the base a of 3 is equal to 0.48. All right, well, I think I'm going to change that to exponential form just to look at it. So a to the 0.48 is equal to 3. Interesting. What can I do with that? Some number to the power of 0.48 is 3. What can I do with that? Well, I'm going to need a calculator for this one. This is definitely a calculator question. But how do I tell my calculator to do that? How do I say to my calculator, hey, give me a number that when I times it by itself, 0.48 times is 3? Any idea? There you go. You should, on your calculator, be able to put in any root number you want, right? Every calculator has a built-in square root button. Some of them even have a built-in cube root button, and that's all that's built in. But somewhere, there should be a button that's the xth root, and you can put in anything you like. I am actually looking for the 0.48th root of 3. Which, by the way, I could change to 3 to the power of 1 over 0.48 if I wanted to. If that's an easier thing for you to punch in, both of those things are the same thing. So, yeah, try it on your calculator. I think you get 9 point something. What did you get? 9.8. Yeah, that's the one. So A turns out to be 9.863. Try that on your calculator, see if you can make it work. This button is usually on most calculators, the shift of the exponent button. So if you have a button that is x to some power like that, or x to the hat, or it's x to the y, or something like that, that button you use to do a number to the power of 4 or 7 or whatever, the inverse of that button, the shift of that button, is usually your root button. So give it a try. See if you can make this answer on your calculator. And that's basically it for 8.3. So now, let me go to the workbook. Actually, I could stop the video too. So that's it for the notes. Go to my video and stop recording.